Section 1 Introduction. In this paper, we delve into the fascinating world of large language models and their ability to perform few-shot learning. This is a process where the model is given a few examples and then asked to generate a response. This capability has been demonstrated not only in language tasks but also in other domains, thanks to the underlying technology of transformer models. These models have shown an impressive ability to learn complex, high-dimensional, and nonlinear functions from a few examples. In fact, they often match or even surpass the performance of other machine learning models specifically designed for these tasks. For instance, it has been shown that a transformer network can learn unseen sparse linear functions as effectively as the lasso, a method known for its optimal performance in modeling data, after being pre-trained on sparse linear data. However, the key to unlocking this capability lies in the pre-training process, where the model is taught how to perform in-context learning using relevant data. In this study, we focus on the data used in this pre-training process and explore how it impacts the few-shot learning abilities of the resulting transformer model. We study a specific few-shot learning setup where the goal is to use a small set of provided inputs and labels to predict the label for a new input. This is done by passing the examples in sequentially, alternating inputs and labels, and then passing the test input point as the final element of the sequence. The model's prediction for the next item in the sequence is treated as the predicted label. We also investigate how the composition of pre-training data affects the ability of transformers to learn related tasks in a few-shot manner. Our findings reveal that the model can perform model selection among pre-trained function classes during in-context learning with little extra statistical cost. However, there is limited evidence that the model's in-context learning behavior can generalize beyond their pre-training data. Transformers are sequence models that provide next token predictions based on the previous sequence tokens. We frame the in-context learning problem as providing a single prompt sequence to the model and generating a prediction for the next token. The performance of an in-context learner is judged by its predictive squared loss, with the expectation taken over the randomness in the prompt and query. We pre-train the transformer model on simulated prompts represented as sequences. The model is then able to learn unseen functions drawn from the same function class at test time. For example, transformers pre-trained on data generated from linear functions, decision trees, and ReLU networks are able to perform as well as state-of-the-art machine learning methods on these respective function classes. We also explore the role of pre-training function diversity for in-context learning in the setting of pure linear regression. We argue that a sufficiently diverse distribution over linear tasks in pre-training is needed for in-context learning at test time. Finally, we investigate how the construction of the data source affects the in-context learning abilities of the model. We use data mixtures which combine together examples generated from multiple distinct function families. We consider several distributions over base function classes: dense linear functions, sparse linear functions with non-zero coordinates, two-layer ReLU networks, and sinusoidal functions. We also explore how these models perform on examples that are out of distribution from the training data. We interpret the generalization question as, can a model generate good predictions with in-context examples from a function not in any of the base function classes seen in the pre-training data mixture? We first study the abilities of transformers to perform model selection between different function class families seen in pre-training and then transition to answering the out-of-distribution generalization question for a few important cases. Section Summary. Large language models, such as transformer models, have shown impressive few-shot learning capabilities by learning high-dimensional and nonlinear functions from in-context examples. In this work, the authors investigate how the composition of the pre-training data affects the few-shot learning abilities of transformer models. They find that the models can perform model selection among pre-trained function classes during in-context learning, but there is limited evidence that the models can generalize beyond their pre-training data. Section 3 Model Selection Phenomena. In this section, we're going to explore a question that often arises when we're dealing with a mixture of different function classes during pre-training. The question is, how does the model choose between these different function classes when it encounters examples that are within the range of the pre-training mixture? We're going to tackle this question from an empirical standpoint, focusing on the observable phenomena rather than the underlying mechanisms. We believe it's crucial to first document these phenomena clearly for the benefit of the research community. We've found that after being exposed to examples from a function class that's part of the pre-training data mixture, the models make optimal, or near optimal, predictions. We've also observed how models perform on functions that don't neatly fit into any single component function class, and we've explored some functions that are definitely outside the range of all pre-training data. We started our investigation with linear functions, which have been the focus of much attention in this area of in-context learning. We found that transformers pre-trained on linear functions perform almost optimally when learning in context on new linear functions. We considered two models, one trained on dense linear functions, where all the coefficients of the linear model are non-zero, and one trained on sparse linear functions, where only 2 out of 20 coefficients are non-zero. Each model performs as well as linear regression and lasso regression on new dense and sparse linear functions, respectively. We also compared these two models to a model pre-trained on a mixture of both sparse and dense linear functions. We found that the model pre-trained on this mixture performs similarly to the models pre-trained on only one function class. This suggests that this model is nearly optimal. We also found that this model's ability to select in context is relatively consistent, regardless of the number of in-context examples provided. We also observed that the model's performance on pre-training data mixtures with various non-trivial weights for a given function class nearly matches the optimal baseline sample complexity compared to pre-training a model purely on that function class. We noticed only small deviations, and these quickly decrease as the number of in-context examples increases. However, we also found that the transformer model's generalization suffers when it's out of distribution. For example, even though dense and sparse linear classes are both linear functions, a transformer pre-trained only on sparse linear functions performs poorly when evaluated on dense linear data, and vice versa. We also briefly explored the effect of model size on model selection. We found that the model pre-trained on the mixture performs as well as the models pre-trained on the mixture components. This suggests that the model is capable of choosing whether to make predictions using knowledge solely from one base function class in the pre-training mixture or the other. However, when the number of non-zero coefficients is approximately 4, the mixture predictions deviate from both those of the purely dense or purely sparse pre-trained transformer. This suggests the model pre-trained on the mixture is not simply selecting a single function class for the predictions, but predicting something in between. We also examined the in-context learning, ICL, generalization capabilities of models along two axes. First, we explored and tested ICL performance on functions the model has both never seen in training and also could plausibly predict. Convex combinations of functions drawn from the pre-training function classes. Second, we evaluated ICL performance on functions which are extreme versions of functions seen in pre-training. In both cases, we found little evidence of out-of-distribution generalization. When the function is significantly different from those seen during pre-training, the predictions are erratic. However, when the function is sufficiently close to the pre-training data, the model approximates it well with predictions from the function classes on which it was pre-trained. We also found that the model's ability to select the best function class for predictions is limited by proximity to the pre-training data. This suggests that broad coverage of function space is critical for generalized in-context learning capabilities. Finally, we found that the model's generalization starts strong and then degrades dramatically as the tasks become so rare as to be out of distribution. Specifically, we trained models on a mixture of sinusoids with frequencies drawn from a distribution that ensures that the average frequency is 1. Frequencies below 0.01 or above 5 are extremely rare. We observed the predictions from all of the models on a variety of frequencies inside and outside this range.